Welcome, dear learners. In this video of molecular spectroscopy, we will discuss some basic concepts related to molecular spectroscopy. Let us first discuss what is the definition of spectroscopy. Spectroscopy is a branch of science which deals with the study of interactions of electromagnetic radiations with matter or material. So basically it is nothing but the study of interactions between electromagnetic radiations and any material or matter present surrounding us. Now, what is electromagnetic radiations? The term electromagnetic radiation represents the gradient energy emitted from any source in the form of light or heat, etc. Now, what are the characteristics of electromagnetic radiations? Electromagnetic radiations have dual nature, that is wave as well as particle. These waves are associated with electric and magnetic field perpendicular to each other and to the direction of propagation of light, as it is indicated in this diagram. So this diagram consists of three-dimensional Cartesian coordinate system x, y and z, and if we draw a wave that is propagating on x-axis, then electric field is oriented on z-axis and the magnetic field is oriented on y-axis, and x-axis is used to denote the direction of propagation of the wave. That means these three things, that is electric field associated with the wave, magnetic field associated with the wave, and the direction of propagation of the wave, they are exactly perpendicular to each other. All electromagnetic radiation travels with the velocity of light. So velocity of all electromagnetic radiation is equal to the velocity of light, and that is one of the fastest moving object in the universe. And the value of this speed of light is 3 into 10 raised to 8 meter per second. Each photon is consist of a packet of energy, and it is calculated by Planck's equation E is equal to h mu, where h is Planck's constant, E is energy of that electromagnetic radiation, and mu is frequency. So these are some basic characteristics associated with electromagnetic radiations. Now, we use some terms to define electromagnetic radiations, and these terms are highly basic. We discuss it quickly. Wavelength. The distance between two successive trough or crest is called as wavelength. So, a transverse wave consists of crest and trough, and the distance between two successive crest and trough is called as wavelength. The unit used to measure wavelength is either angstrom, nanometer, micron, millimeter, and centimeter according to the wave. What is wave number? Wave number is very commonly used term in as far as molecular spectroscopy is considered. According to the concept, the wave number is simply the reciprocal of wavelength. Therefore, the unit of wave number is simply the reciprocal of unit of wavelength, that is centimeter inverse, nanometer inverse, or millimeter inverse, etc. Next term is frequency. The number of waves passing through a point per second, that is called as frequency, and the unit of frequency is cycle per second, or it is also called as hertz. Now, electromagnetic radiations, if you consider the electromagnetic spectrum, it consists of different regions. So following slide represent the different regions of electromagnetic radiations. So all these regions, they are arranged with decrease in energy or increase in wavelength. So the first region of electromagnetic spectrum is cosmic ray. It is highly energetic region whose wavelength range is 0.001 angstrom. Frequency is in the range 3 into 10 raised to minus 21, and it is present in the outer space of the Earth. Next region is gamma ray, whose wavelength is 0.0001 to zero point 0.1 angstrom, and its frequency is 3 into 10 raised to 22 to 3 into 10 raised to 19, and the source of this gamma ray is radioactive substances. Next region of electromagnetic spectrum is X-ray, and whose wavelength is 0.001 to 100 angstrom, and frequency is 3 into 10 raised to 20 to 3 into 10 raised to 12. And X-rays are emitted by the bombardment of certain metal with cathode rays. Then we have ultraviolet rays, whose wavelength is 1 to 3800 angstrom, and the frequency range is 3 into 10 raised to 12 to 7.9 into 10 raised to 14. Hydrogen or deuterium discharge tube, or a component of sun rays, is a source of ultraviolet rays. Next, visible region, 3800 to 7600, that is the wavelength range. 7.9 into 10 raised to 14 to 4 into 10 raised to 14 is the frequency, and the source is a sun or any filament line, tungsten filament line. Infrared, next to visible, energy of infrared rays is slightly less than visible, and when infrared rays are used, then the molecules show vibrations, and it is produced by the heating rod of some special material. We will discuss the source in the latter part of this presentation. Then after infrared, next region is microwave, and it is produced by the oscillation of electron in an wire, that is from alternating electric current. After that, last region is a radio wave, or it is also called as communication wave, having lowest energy and highest wavelength. Now again, this slide gives us information about different parameters such as wavelength, wave number associated with different regions of electromagnetic spectrum. Now, introduction to molecular spectroscopy. In case of molecule, when the energy is absorbed, it may result into the rotation, vibration, or electronic transition. So this is the simple response given by any material to particular electromagnetic radiations. So when material is exposed to electromagnetic radiations, either the molecule show rotations, vibrations, or electronic transitions observed in the molecule, and it is depend on the energy associated with that particular radiations. Just as electronic energy is quantized, the rotational and vibrational energies are also quantized. The rotational, vibrational, and electronic energy level of the molecule are collectively called molecular energy. So molecular energy is simply the energy associated with molecule, and it is nothing but the sum of rotational, vibrational, and electronic energy. Transition of energies can take place only between these energy levels. So molecules are arranged in different energy levels, and during transition, it jumps from one energy level to another energy level. And this transition results into the molecular spectrum. So in this way, energy levels are arranged, and the transition from one level to another level takes place by absorbing energy from particular radiations. Now, spectroscopy can be broadly divided into two types: absorption spectroscopy and emission spectroscopy. The transition may take place from lower energy level to higher energy level by absorbing energy, and it is called as absorption spectroscopy. Or we can simply say that in case of absorption spectroscopy, radiations are absorbed, and which results into the transition from lower energy level to higher energy level. And the type of this absorption spectroscopy is X-ray diffraction spectroscopy, UV spectroscopy, infrared spectroscopy, microwave spectroscopy, and NMR spectroscopy. Now, second type is emission spectroscopy. The transition may take place from higher energy level to lower energy level by emitting the excess amount of energy by the photon. So, if the molecule is already in excited state, then it emits energy and come to ground state or comes to lower energy state. So, the transition from higher energy state to lower energy state via emission of excess energy is observed in this type of spectroscopy, that is called as emission spectroscopy. Raman spectroscopy and fluorescence spectroscopy are the type of emission spectroscopies. It is shown with the help of a diagram. See here, first is the absorption spectroscopy, in which radiation is absorbed, and from E1 energy level, molecule jumps into E2 energy levels. That is called as absorption spectroscopy. Now, in emission spectroscopy, molecular is at higher energy level, that is E2. It comes to lower energy level via emission of the radiation, that is called as emission spectroscopy, and the energy of the photon h mu emitted or absorbed is given by Bohr's frequency formula, that is E2 minus E1 is equal to h mu, and we know that lambda is equal to c upon mu. Therefore, by putting the value, we can write hc upon E2 minus E1. In this way, we can calculate the wavelength of that uh, emitted light. Now, Born-Oppenheimer approximation. This is a very important concept. A molecule usually possesses four different types of energies, such as translational, rotational, vibrational, and electronic energies. So these are the four different types of energies associated with any molecule. And according to Born-Oppenheimer approximation, the total energy of the molecule is the sum of translational, rotational, vibrational, and electronic energies. Therefore, in terms of mathematical formula, we can write E is equal to energy, translational energy plus rotational energy denoted by ER, vibrational energy denoted by EV, and electronic energy denoted by EE. And it is observed that the translational energy is negligible, therefore it can be neglected, and we get the new equation: total energy of the molecule is equal to vibrational energy, rotational energy, and electronic energy. This is called as Born-Oppenheimer approximation. Next, a type of molecular spectra. The energy absorbed for any transition is equal to the difference in the energy of the two levels that is involved, and it is found that these energies for transitions are in the order: the transition energy is less than rotational energy is less than vibrational energy, and vibrational energy is less than electronic energy. So the translational energy is considered as continuous, and we do not observe any translational spectrum. Now, pure rotational spectra or microwave spectrum. When a material is exposed to microwave radiations, then it shows rotation. So only rotation is observed in microwave region. Therefore, it is also called as microwave spectra. During this rotation, there is a transition in energy level which results in the spectra, that is called as microwave spectra, or it is also called as pure rotational spectra. While in infrared region, vibrational rotation spectra is observed because the energy of infrared region is more than microwave region. Therefore, due to the more extra energy associated with infrared region, it produces rotation as well as vibration in the molecule. Therefore, the spectra obtained in infrared region is called as rotational vibrational spectra, and that is observed in IR spectroscopy. Then electronic spectra or UV spectra. These spectra are observed in visible region, and due to the high energy of these ultraviolet radiations, the electron show excitations from bonding, non-bonding, anti-bonding to its higher energy states. Raman spectra. This is also a type of vibrational rotational spectrum. It is based on scattering of radiation and not on the absorption of radiation by the sample. Raman spectra is observed in visible region. Then we have nuclear magnetic resonance (NMR). This type of spectra arises from the transition between nuclear spin energy levels of the molecule when an external field is applied in this region. So this spectra is observed in radio frequency region. NMR spectra observed in radio frequency regions. Then ESR, electron spin resonance spectra. This type of spectrum arises from the transition between the electron spin energy level of the molecule when an external magnetic field is applied in presence of microwave radiations. So these are the different types of spectroscopy techniques and how the molecule respond to particular radiation is discussed in these two slides. Now, different types of typical spectrometer. Spectrometer is an instrument that is used to record and analyze the response given by the sample to particular electromagnetic radiations. And we have different types of spectrometer such as UV spectrometer, UV visible spectrophotometer, IR spectrophotometer, etc. So all these spectrometers uh, contain some common components or some common parts, and these are the name of different common parts and how they are connected, interlinked with each other. So the first important part of any spectrometer is radiation source. Radiation source is connected to the filter or monochromator, followed by sample holder. Then sample holder is connected to detector. Detector is connected to amplifier or recorder. And at the last, we have display unit, that is a computer screen. Now we will discuss all these components one by one. First is the radiation source. In UV visible radiations, hydrogen or deuterium lamp is used as a radiation source for ultraviolet rays. It consists of hollow bulb containing a pure electrode and it is filled with hydrogen or deuterium. When high voltage is applied, it emits radiation in the region 180 nanometer to 350 nanometers. Now, the radiation source used in visible spectroscopy or UV visible spectroscopy. So, for visible radiation source, tungsten filament lamp is used. It is cheap, inexpensive, and it emits radiation in the region 350 nanometer to 2500 nanometer. IR radiation source. Nurse glower and glow bar are the two lamps used for IR radiation source. Nurse glower consists of silicon carbide rod heated at 1200 degrees Celsius, while glow bar consists of zirconium rod heated at 1500 degrees Celsius. Next important component of a typical spectrometer is wavelength selector. We have two types of wavelength selector, filters or monochromators. Filters generally consisting of a glass slit which absorb maximum part of radiations and transmit the required radiations. Some filters consist of a gelatin filled between two glass slits. So in colorimeter and in sunglasses we use filters to remove unwanted radiations. Another type of the wavelength selector is monochromator. We know that the visible light consists of 7 different colors, and monochromator is used to resolve polychromatic light into monochromatic light. So in monochromator, prism is used which resolves the light into its different constituent color, and by the process called as refraction. And after resolution, a particular light radiation is used for further analysis. So that is the use of this monochromator in this wavelength selector. Another type of wavelength selector is another type of monochromator is grating. It consists of highly refractive surface which can also resolve light into 7 different colors. So a compact disc is associated with this grating. Next is sample holder. In UV, we use a glass tube as a sample holder, which is also called as cuvette, while in IR spectroscopy, depending upon the physical state of the sample holder changes. For gas, a gas cell is used and it is made up of KBr. For liquid sample, a thin film of liquid is prepared between KBr plates, while for solid, pellets or tablets is prepared in KBr for further analysis. Next component is the detector. In UV visible spectroscopy, photocell, phototubes, and photomultiplier detectors are used, while in IR spectroscopy, thermocouple, bolometer, and gas thermometers are used as a detector. So this is all about different types, different components of typical spectrophotometer. Thank you.